So let's go back to the conventional definitions of phase and gain margin. And we now come to the very interesting question, how much phase margin is necessary? And I always like talking about this to working engineers who've got some experience and asking you that question. What's your view? What was the first one? 60 degrees, 45 degrees. Yeah. Okay. Well, I didn't hear any lower than 45, which is nice. But now there's some comments to do with the fact that it depends on some other things, such as did I hear transient response? Okay, and there was something else is to do with how the loop gain crosses over. In other words, there's something more to the question, because simply how many degrees of phase margin you have doesn't seem to be really what the important answer. And that's true. What really matters is not simply is it stable, because it's stable even if there's only 1 degree of phase margin. What is more important is what is the response of the system relative to the specifications. So the most important property of the feedback system is its closed loop gain G, which is G infinity times D. Now G infinity is designed in right away according to the specification, and the feedback path is designed to do that. What's important is how close is G to the G infinity. And that's what the discrepancy factor is about. The discrepancy factor is a unique function of T. The phase margin is a property of T. So the phase margin is inside the D as well. So there is something to do with the relationship between the phase margin and the shape of D, which is going to determine how closely the gain follows the specification. So the proper question is not just as some sort of arbitrary absolute number, how many degrees of phase margin do you need? The proper question is, what is the relationship between the phase margin of T and the shape of D, which determines the shape of the closed loop response? That's the real question to ask. Now, even that isn't the only question, because what really matters is not the nominal shape of D. What really matters is worst case shape of D, because you have a tolerance on the specification and you have tolerances on the components that you're going to build into your system. So what really matters is that you have to meet the specification tolerance under the worst case combination of component tolerances. So what matters is the minimum phase margin under worst case conditions. Just as an example, if you have one design that gives you a nominal phase margin of 30 degrees, and it never gets worse than 25, and compare that design with a nominal phase margin of 70 degrees, but it can get as bad as 15, that's worse. So you've got to be, it's really the worst case that matters. Now that part of the answer you can't give in general, because it depends on the sensitivity of the phase margin to the component tolerances, and there's nothing you can say about that in general without going to the specific design. But it's certainly an important thing that you have to bear in mind, and we'll see an example of that. So there's not much we can say about it other than to recognize you have to take that into account. So let's go back to the first part of the answer, which you can answer in general, because of a unique relationship between phase margin and discrepancy factor. Since it's unique, we can say something about it in the general case. So let's start working on that. Let's start, as usual, with the simplest case. A single pole loop gain, Tm flat value, pole at omega 1. The discrepancy factor that corresponds to it is T over F. And we've gone through this construction now a couple of times. And we know the result for D is a line just a little bit less than 0 dB, Tm over 1 plus Tm. And it has a single pole which is on the same asymptote as the original T. And the next step is you multiply the D by the G infinity to get the closed loop gain. Well, we don't need to go through that step anymore at the moment because it's the shape of D that is going to determine that result. And the objective is to get D as close to 1 as you can, which you do by making the loop gain large. However, you still have to account for the fact that it's going to go away eventually. So the closed loop gain that you get for this case is a flat value and a single pole, which of course actually has a 3 dB smooth corner. Now that's the ideal case. That's the best possible shape for D that you can ever get, given that it's going to roll off somewhere. So flat up to a certain frequency and then a smooth 3 dB corner is the best you can do. In other words, it's the most graceful roll-off of the closed loop gain you can get, where it begins to deviate from the G infinity. What's the phase margin in this case? About 90 degrees. Assuming you're far enough down this slope, the phase angle of T is almost 90 degrees, which is 90 degrees less than the critical 180, so the phase margin is 90 degrees. Just qualitatively. So we associate a phase margin of 90 degrees with an almost ideal shape of discrepancy factor. Now that's the simple case. We want to talk about what happens if the phase margin is less than 90 degrees, which means we have to consider the possibility of a second pole in the loop gain, because that's what will eat up the phase margin. So we're going to make the problem a little more complicated. Now let's remember, never put more in the problem than is necessary to get the answer you want. It's going to clutter it up, make it more difficult, obscure the results. Let's get rid of some unnecessary parts of this problem before we make it more complicated again. Now, we're concerned only with the shape of D. And the only important part of that is near the crossover frequency of the loop gain. Because as long as the loop gain is large at lower frequencies, the shape of D is going to be close to 0 dB, which is where we want it to be. In other words, suppose there were a much more complicated shape of T down here. Suppose there was some more corner frequencies. What would happen to D? It would get little wiggles in it. But we don't care about those. And the higher the loop gain, where the wiggles, where the corners occur, the closer the wiggles would be to 0 dB, and the smaller they would get, and we don't care about them anyway. So we can simplify the problem by going in the other direction, leaving out the corner frequency that's there already. That is, pushing it off the picture. What happens to D if we do that? It gets to 0 dB, flat. That's a simpler case. And we don't need to worry about the little wiggles anyway. So let's simplify the problem by pushing the omega 1 corner off the picture. And we can do it graphically, which is basically what I just done, or you can actually set it up analytically by changing the parameter which we used to represent the original T. That is, by gain bandwidth trade-off, the crossover frequency omega 0 is equal to Tm times omega 1. So get rid of Tm by using that substitution. Or I should say get rid of omega 1 by using that substitution, which converts the formula for T into this one. Then push Tm off to infinity, which gets rid of this term, and you're left with just 1 over S over omega 0, which is this single slope with unity magnitude at the frequency omega 0, which we've already done several times as well. And at the same time, rewrite the D to get rid of the omega 1, and then let Tn go to infinity in that one, and you get 1 over 1 plus S over omega 0, which means that the D has approached 0 dB and its corner frequency has approached omega 0. So the whole thing comes down to that. So we start with the simplest possible problem, which is a single asymptote for T, and we don't care where it came from at low frequencies. And the corresponding closed loop gain, which is proportional to the D, is going to be 0 dB with a pole at omega 0. So we've simplified the basic problem, stripped it down to the only essentials we're interested in, which is what happens to the shape of D near crossover. Now we're in a simpler position to start making the problem more complicated in a useful manner, which is to consider what happens if you have a second pole in T. Now, if the second pole is a long way above the original crossover, then D is equal to T whenever T is small, so D will have the same pole that T does. And here's the formula for T. The original single slope crossing unity magnitude at omega 0, and then you have a second pole at omega 2. Now, qualitatively, again, looking ahead to what the result is, this is not quite such a graceful roll-off for D, because it's going to roll off a little more rapidly than before. What's the phase margin now? Qualitatively. It's less than 90 degrees. You evaluate the phase lag at crossover, which is minus 90 degrees from the first slope of T, and then there's a little bit of extra contribution from the second pole that's further up. So the phase lag is a bit more than 90 degrees at crossover, therefore the phase margin is a bit less than 90 degrees. So you associate a phase margin less than 90 degrees with a little less desirable shape of the closed loop gain. Now the interesting part comes in when you let the second pole get closer and closer to the original crossover. And we want to know what happens to the shape of D as you do that. And so we've now set up a very limited and simple little analytical problem. We know what the formula for T is, in which the omega 2 can be any number. It doesn't have to be much higher than the omega 0. All we have to do is plug into the relationship the unique relationship between D and T. And so when you plug in the T with a second pole, this is what you get. And you see immediately it's a quadratic. And now you should have that automatic response. Whenever you see a quadratic, find its corner frequency and its Q factor. So write it in the normalized form, and in order to do that, you have to define the corner frequency omega c is the square root of omega 0 omega 2, and the Q factor is root omega 0 over omega 2. That's exactly the same quadratic that we spent a lot of time talking about in relationship to an RLC filter. But as I anticipated at the time, even though you may not care about RLC filters, it's still worthwhile knowing about the quadratic equation, because here it shows up again even though there's no inductance in sight. And it arises as part of a rather important problem to do with the shape of the closed loop response. But now we already know about all the possible shapes of the quadratic relative to the value of Q. So we want to see what value can Q take. And since the omega 0 is being kept fixed and the omega 2 is a parameter that's variable, it can have any value, so Q can have any value. So what we need to do is to look into the various possibilities, represented by a typical case for each of the useful ranges of Q, namely high Q and low Q. And maybe one in between, depending on whether Q equals 1 is important or Q equals 0.5 is important. So let's look at the useful cases. The simplest one is what happens when Q is much less than 0.5, which would mean the omega 2 is a long way above the omega 0. And that's the case we already anticipated. Because if Q is much less than 0.5, you can factor the quadratic into the two approximate real roots, of which the first one is the first two terms, which is the omega 0 pole, and the second one turns out to be the second pole in T. So as we already expected, the shape of D has two real roots at Q omega c and omega c over Q relative to the corner frequency, and the corner frequency is the geometric mean between omega 0 and omega 2 by its definition. And the Q omega c is omega 0, and the omega c over Q is omega 2. So that's the shape of the D you get in the low Q case for its quadratic. Now the next interesting case is, what if Q is 1? Q is 1 if the omega 2 comes back down to be equal to omega 0. So the second pole in T is at the original crossover frequency. So the shape of the quadratic with a Q of 1 means that D is 0 dB and goes through unity at the corner frequency and bulges up a little bit below it, and then bulges up above the other asymptote and falls off at a double slope. Now remember what D is telling us. This is the shape of your closed loop response relative to the specification. So it means your closed loop response is beginning to build up a little bit into a peak. And you've got to keep that within the tolerance of your specification. What's the phase margin now? Yeah, about 45 degrees. Because at the crossover, again, you get 90 degrees from the initial slope, and you're right at the second corner, so the second pole is giving you another 45, so the total phase lag is 135, and the phase margin is 45. So now you associate a 45 degree phase margin with a closed loop response which is beginning to peak up. Well, what happens if you go to an even bigger Q, which is what happens if the second pole in T comes in even before the original crossover? So now you're crossing over on a double slope. And now the quadratic representing the closed loop response D peaks up significantly for a high Q. And the geometry is such that at the corner frequency of the quadratic, the closed loop response actually goes through the point that lies on the asymptote of the original slope. You can check that on your own if you like, to do with the relationship between the geometry and the roots of the quadratic. But the important part is simply to look at the picture. Because for sure, this isn't going to meet your specification. And of course the phase margin is now below 45 degrees. So right now we've solved a little local analytical problem to find the relationship between the position of the second pole in the loop gain and the resulting shape of the closed loop discrepancy factor. There's another half of the analysis to go through, which is to quantify the relationship between phase margin and Q. So far I've just asked you qualitatively at each case what's the phase margin, but we can actually get a quantitative result. Here's how we do it. Here's the general case, where I've drawn the second pole in T a little bit above the original crossover at omega 0. All I have to do is calculate the phase margin using its definition. The phase margin is defined in terms of the phase lag of the loop gain at the crossover frequency. Now, this is one of the rare cases where you actually have to account for the smooth curve at the corner, and the asymptote itself is not sufficient. The reason being that we want to allow omega 2 to move through omega 0. In other words, the smooth corner is going to move through the axis, and the crossover frequency is really the frequency where the actual curve crosses unity magnitude, not where the asymptote crosses. So omega m is the true crossover frequency at which we want to evaluate the phase margin. So the first thing we do is evaluate the crossover frequency in terms of the position of the second pole. So it's useful to have the Q as a parameter now instead of the omega 2, because the Q is the quantity that comes up in the answer we're interested in, which is the shape of the D. So let's substitute the variable. Instead of omega 2 being the variable, now Q is the variable, which we get by inverting the definition of the Q. Q was the root omega 0 over omega 2, which means inverting it, omega 2 is omega 0 over Q squared. So I've simply made the substitution in the formula for T. So Q is now the parameter. Again, this is an example of introducing into the problem at the beginning the parameters that you want to have in the answer. And since Q is the thing we're interested in, because that determines how much peaking we get in the closed loop response, let's put the Q in right at the beginning. And it now replaces the original position of the second pole. Okay? All you have to go through is a little straightforward analysis now to solve this expression for the value of the frequency when the magnitude of T equals 1. So you set the magnitude squared of T equal to 1, and this is the magnitude squared of the right-hand side. And this occurs at the crossover frequency omega m, so you have to invert this and solve for omega m. And you find that it's a quadratic in omega m squared. And using the new version of the quadratic solution, the relevant root is minus c over b coefficient 1 over f, where f is this function we talked about before. The quadratic has two roots, but this is the only one that's relevant because the other one comes out negative. And since it's the square of something, that one is irrelevant. So this is the only one that matters. So this is the result for the crossover frequency relative to omega 0 as a function of Q. Check that it goes to omega 0 if Q gets very small, because if Q gets very small, this corner moves off to the right, and omega m ought to approach omega 0, which it does. If you let Q go to 0, the ratio goes to 1. Okay, all that's left now is, now we have solved for omega m in terms of the position of the second pole, and now you evaluate the phase margin, which is 180 plus the angle of t evaluated at the crossover frequency, which is minus 90 degrees from the first asymptote, and then minus arctangent of the crossover frequency divided by the second pole. It's how you find any phase angle from a single pole function. This is the omega 2. And when we substitute for the omega m that we just solved for, you get this. So this is the relationship between phase margin and the peaking factor of your closed loop gain. And you can invert that expression and get this one. And that's the bottom line. Now, you don't learn much by looking at that equation. You learn a lot more by looking at the graph of that equation. I don't want to see the top part. I want to get the axis in it. Okay, this is the graph of that equation, and I marked 3 interesting points on it. A Q of 1 means that your closed loop discrepancy factor is just beginning to peak up a little, and it corresponds to a phase margin of 52 degrees. Now, that's sort of a dividing line, isn't it? You don't want the Q to get any bigger than that, otherwise for sure you're going to be out of spec. If you want to be really safe, and you want the Q to be no bigger than 0.5, which means your closed loop quadratic has 2 equal real roots, and you're 6 dB down at the end of your closed loop bandwidth, you've got to have 76 degrees of phase margin. If you go in the other direction, and when I asked the question at the very beginning of this section, how much phase margin do you think is necessary, I was pleased to hear no one said anything as low as 30 degrees. Because look what happens. 28 degrees gives you a Q factor of 2. 6 dB of peaking in your closed loop response. This is a very interesting graph, because it gives you a quantitative idea of what a certain phase margin number really means. So the number of degrees means nothing in itself. What matters is what is the degree of peaking you're going to get in your closed loop response. And the important thing about this result is it's inescapable. There's nothing you can do about this, because we haven't said a word about the design or what kind of feedback amplifier it is. This is absolutely general. There's nothing you can do about it. So this is a very useful graph, and especially if you remember this critical point. Q of 1 requires a phase margin of 52 degrees, and I would tend to translate that into something to remember, that you never want to let your phase margin get less than 52 degrees. Worst case. Not nominal, worst case. Now that may be tough to do. That doesn't do anything to invalidate this. Yeah, it's tough. You've got to live with it. So, if you haven't seen this before, don't blame me for it. There's no point in shooting the messenger that brings the bad news. You've got to live with this. Okay, well, looking at this picture showing the peaking factor, the Q factor of the closed loop response as a function of the phase margin, which is a property of the loop gain. And the important thing is how much phase margin you need in order to get an acceptable response. There's a one-to-one relationship between frequency domain, which is what this Q factor refers to, that is peaking in the frequency domain, that is at the end of the closed loop bandwidth, you may get peaking according to the value of this Q. There's a relationship between that response and the time domain response. So there's a corresponding result, which in fact was brought out at the beginning of all this, which arises when you consider that the transient response of your system also is influenced by the phase margin, and for the same reason. The way you look at transient response is, if you have a step function applied to the front end of your amplifier, then you find the transient response of its output voltage by taking the inverse transform of the step, which is 1 over S, times the transform of the gain of the system. And the transform of the gain of the system is simply the gain we already have as a function of S, which, as we've seen, is a quadratic in the denominator coming from the discrepancy factor. The G infinity I've kept out front. In fact, it doesn't matter in this case because we're assuming that the G infinity is a constant. So there's no transient response associated with it. So the time response of the output voltage of your amplifier is proportional to the time response of the discrepancy factor, and it's this function in the case of the two-pole loop gain. So to find what that looks like, you go and dust off your book of Laplace transforms and flip a few pages till you find this one, and this is what you discover, which is a long equation, but all it says is that it's a damped sinusoid. And it looks like this, starting from 0. And it's normalized to unity input step, so that's the final steady state value of the output. And if you have a high Q, then the output overshoots and rings. And the important part of it usually is what is the initial overshoot, and you can find that pretty easily, and it's I called it D1, the first peak, and it's a function of Q. And here's its value for a couple of interesting cases. The sort of transition case where Q is equal to 1, corresponding to a phase margin of 52 degrees, and the consequence of that is you get a 16% overshoot in the time domain, which isn't that much, and that's why it corresponds to the transition case where a little bit of peaking corresponding to Q of 1 isn't bad. Compare that with the worst case where the phase margin is only 28 degrees with a Q of 6 dB, and that gives you 44% overshoot. Again, probably not acceptable, just as the frequency response peak of 6 dB probably wouldn't be acceptable either. So that wraps up the discussion of the relationship between phase margin and closed loop response. There's not much point in treating any more complicated cases, that is, what would happen if you had 3 poles, for example, in the loop gain, because you've got too many parameters to deal with then, and there's no point in making page after page of normalized graphs. The only thing you know about it, of course, is that it will be worse. So that's not much help anyway. Now I want to look at a related problem. And this one comes up specifically in the realm of switching power supplies. It's a good exercise anyway at this point. here's a different shape of loop gain, starting from T0, and it has a second order corner. That is, it has a complex pair of poles, which might arise from a real LC filter, which is part of every switching power supply. And if you close a feedback loop around that switching converter in order to make a switching regulator out of it, then the loop gain is proportional to the transfer function of that LC filter. In other words, the LC filter characteristic shows up as part of the loop gain, which is why it's shown right here. If you don't do anything else to do with frequency compensation, then the loop gain would consist simply of this second order two-pole filter, which means that when you close the loop, you're going to cross over on a double slope, the skirt of the LC filter, and you wouldn't have any phase margin. So you'd be on the verge of instability before you've done anything else at all. So what you have to do is to put a zero in. In fact, I already mentioned this in the progression of how you design a loop gain in order to fill in that window appropriately. So since we already have two poles, you have to put one zero in order to sort of flare out the response and bring the phase lag back down before you get to crossover. So there's an analogous problem now. Where do you put the zero in order to get an acceptable closed loop response for your switching regulator? And again, the first thing to decide is, what is it that characterizes the closed loop response? And it's the same quantity, the D. D determines what the closed loop response is going to look like relative to the specification. So you're concerned with the shape of D again, in this case, just as you are in the case of an amplifier. So it's a very closely related problem, and one that I'd like you to think about for a few minutes to set it up. The steps are the same. Write the factored pole zero form for T, plug it into the expression for D, which is T over 1 plus T, and see what happens to D. See what its shape is, factored pole zero form. See if it has a quadratic. If so, what is it that determines its Q? So it's a parallel problem to the one we've just done. So look at that for a few minutes, and mainly just to the point of setting up the problem, which is writing the expression for the factored pole zero form for T. Well, before you get too far along with that, let me start it off using the flat gain as reference, T equals T0. You look up in frequency and you see a concave downwards corner, which in this case is a double corner. So you represent that by the standard quadratic, and the parameters are already given. So its Q factor is 1 over Q1, S over omega 1 plus S over omega 1 squared. And you keep on looking up, and then there's a concave upwards corner at omega 2, so that's a normal 0. And that's everything. Now we're going to plug that into D equals 1 over 1 plus 1 over T. And you see it's going to get pretty messy. And so what I've done is led you up the garden path, because the proper way to start this is simplify the problem before you write anything. And it's exactly the same simplification that I talked about in the previous case, where we had a single pole followed by a second pole further down. And I started off by saying the only part of interest in the solution is what happens near crossover relative to the position of the zero. That's the interesting part of the problem at the moment. What goes on at much lower frequencies when T is very large anyway is of no interest, because all that does is put tiny little wiggles in the D, which is close to 0 dB anyway, and we're not interested in that. So all this part that goes on down here is of no significance. So, throw it away. So now it's a much simpler problem. And you've got to use a different reference point now because the original T0 is gone. Just as we did in the previous case as well. We got rid of the omega 1 and the Tm and we introduced the omega 0 instead. And we do the same thing here. The omega 0 is the thing that we're going to keep constant. And the omega 2 is going to move around, and that's the effect that we're looking at. So, using the omega 0, the expression for T that we need is omega 0 over S, because this is a declining slope. And because it's a double slope, we'll have to square it. And that identifies the left-hand asymptote, and then we just multiply by the 0. And that's all we need for the T. Now, if you want to know what the relationship is between this version and the first one, then of course we could get the same result algebraically as well. Because what we've done is we've limited the first expression to frequencies that are well above the omega 1. By throwing away that part, we're only interested in the part relevant to higher frequencies, which is equivalent to throwing away this term and this one. Because the denominator will be dominated by the S squared term. And this is now the same result because the T0 times omega 1 squared is equal to omega 0 squared. That's how we get from the gain bandwidth trade-off works here. The ratio of the flat gains between the low frequency value and the axis is T0, and the ratio of the corner frequencies is omega 1 over omega 0 squared, because it's a double slope. And if you make that substitution, you see, T0 omega 1 squared is equal to omega 0 squared. So that's how you get from one version to the other algebraically. But it's much easier to do it on the graph. So I won't let you go any further with that because that's the only important part, setting up the problem. Solving it is easy after you've set it up properly. And that's always the part that gets skipped over when you're learning these things. And you concentrate on the method and the technique and how to extract this answer out of this horribly complex problem. But the real important part is setting it up to be simple in the first place. And you see, all the times I've said this now, simplify the problem before you start, and your reaction to that has always been, well, of course. But you fell right into the trap. And everyone does. And it actually takes a conscious effort to stop and think before you start working something out, is there more in here than is necessary? And it takes some practice to get in the habit of thinking that way. Okay, having done that now, then we have the simplified problem, and the only important variable is the omega 2. So you substitute the simplified version now into the D function, and indeed you do get a quadratic again. And so you define a corner frequency, although as a matter of fact it's already defined, it's omega 0, and you define a Q factor in order to put the quadratic into the usual normalized form. And the Q factor is omega 2 over omega 0. Omega 0 is the fixed reference. Omega 2 is the position of your adjustable 0. And it can have any value, again, from 0 to infinity, depending on the position of the compensating 0. So you sketch the the typical case for each of the ranges. What happens if Q is very small, which means that the compensating zero is well below the original crossover? That means you can factor the quadratic into the two separate real roots, and I've shown it done graphically down here. That means that the two real roots are going to be Q omega 0 and omega 0 over Q. That's the blue asymptotes, the two real roots. But there's also another factor in the numerator, which is a 0, and the position of the 0 is Q omega 0, and that's the green asymptote. And you see that in this limiting case of real roots, one of the roots of the denominator cancels the 0 in the numerator. So the result, which is D, the closed loop discrepancy factor, simply remains flat until you get to the second pole of the denominator, because that's all that's left. And then the closed loop gain will drop off at the single slope. If I superimpose that on top of the original picture of the loop gain, this is the loop gain coming down to extrapolated crossover at omega 0, and this is the position of the compensating 0. And the closed loop gain simply stays flat until the single slope crosses over, and then the closed loop gain follows the T. In other words, as long as Q is low enough to justify the real roots, that is, as long as the omega 2 is low enough down here, the double slope part of it isn't doing anything. And you're back to essentially just crossing over on the single slope, which is the ideal reference case. And that's what has happened in this case here, where Q is low enough, the closed loop discrepancy factor simply stays flat and has a single pole, which is the most graceful way it can roll off. So that's the base case. Now we can also consider the case where the compensating 0 is not that low, so let's move it out to the case where Q is 1. And if Q is 1, then the denominator, which is the blue asymptotes for the quadratic, will have a double corner at omega 0, and at the same time the 0 in the numerator moves out to the same corner for a Q of 1. So now the D is the sum of the blue and the green lines, and the blue curve will actually go through the corner, but the green asymptote will actually have a plus 3 dB point, the smooth corner that goes with the green asymptote. So the combination of the two of them will have a plus 3 dB point at the actual corner. So that's what happens when Q is 1 and the compensating 0 is at the original crossover. And already you see you get a 3 dB peak. And if the corner moves out even further than that, if the 0 moves out further, where you've already crossed over on the double slope, then the closed loop response peaks up significantly as well, and then turns around and follows the T after you encounter the 0. And all that is saying is the compensating 0 was too far out to do any good. You've already crossed over on the double slope with a very small phase margin, which is what causes the big peak. And the 0 doesn't do anything till out here, and it's too late. Now, you can continue this problem in the same way as we did the previous one. You can go and solve the other part of it and find the relationship between the Q factor, which is the position of the compensating 0, and the phase margin. And you get exactly the same equation. Now, I was quite surprised about that when I derived it, because the formula for the D is significantly different for this case. It's got the quadratic in the denominator, but it has a 0 in the numerator as well, which the previous result did not have. It had only the quadratic. So I fully expected when I first worked this out that I would get a different result for the relation between phase margin and Q. So I was surprised when it came out the same. And I remained surprised for several years. Then it finally dawned on me, of course, it ought to be the same. But that's like most things, that when you finally see them, you wonder how you didn't get it long ago. But it takes a very simple little trick to figure out why the answer ought to be the same. If I can find the right picture. Yeah. This is the problem we've just solved, which has the same formula for the relationship between phase margin and Q factor. Now, that relationship is an internal property of this geometry, because it's to do with the relationship between the shape of the loop gain and the axis, which is what determines the D. So, to show that it ought to be the same relationship as the previous problem, all I have to do is show it that it's the same problem. And that's the first problem, where we're coming down on a single slope and we have a second pole further out. So, since the result we got is simply an internal property, it ought to be invariant relative to rotations and translations and inversions, which it is. And the reason the formula looks different is we're using a different reference. Because in this problem, the omega 0 was defined as this point. And in the second problem, we used a different position for reference. So that's why the formula was different, but the answer for the relationship between phase margin and Q is the same, because it had better be the same. So that's one of the things you feel a lot better about once you see the reason why. So, to summarize this point now, we started out by posing the question, how much phase margin is needed? And we decided pretty quickly it wasn't the right question. The right question is, what is the relationship between phase margin and closed loop response? Because that's what has to meet the specifications. And even so, after asking the right question, the answer has two parts. And one part can be answered in general, which is what we've done, because there is a unique relationship between the phase margin and the closed loop response. The other part of the answer you can't answer in general because it's to do with sensitivities and worst case. But you just have to bear in mind that you have to be careful about that. And that leads into another little horror story. And if I can find the right. Here we are. This second problem that we've just talked about, which, as I've said, arises from switch mode regulators. And the story is that some time ago there was a small company that built switching power supplies, and they did it very successfully for a long time. And all of a sudden, the customers started sending units back again, saying that some of the units are oscillating, especially at high frequencies. And they couldn't figure out what was different, because they hadn't changed anything. Design hadn't changed, specs hadn't changed, the production line was just still the same. Of course, this is the worst kind of problem any company can have, is when the customer sends things back and you can't figure out what's wrong. But of course, it requires an immediate crash program to find out. And it took them a long time to discover anything that was different from the way they were doing it before. And finally, they found that the only thing that was different was that they started buying the output capacitor from a different vendor. Now, by looking at this picture, you get an idea why that made a difference. The trouble is, they had not looked at this picture because they hadn't done this analysis in the first place. The design had been done by the traditional method of twiddle the knobs on the bench until it works, draw it on the diagram, and send it off to production. And they didn't oscillate, so they said fine, and they went on producing them. But what had happened when they started using a different capacitor was that the reason they didn't oscillate in the first place was because the capacitor they were using puts a zero in this response. We did that already. That was one of the extensions of the original RLC filter. The last thing we put in was the capacitor ESR, and we found out it produces an additional zero. And that's what was stabilizing the loop, because it put this zero in at a nice low frequency, and so they built a good phase margin. And then when they started buying the capacitor from a different place, the ESR was lower, and the zero moved out, so they didn't have as much stability margin as before, and moreover, ESR goes down as temperature goes up. So at high temperatures, the corner moved even further out, and sometimes it moved out far enough that the stability margin went away altogether, and they had an oscillator on their hands, and an unhappy customer. This is an example not only of the hazards of putting a design out without even doing the analysis, but in this particular case it emphasizes the importance of the worst case, because they had also violated the other principle of design, which is don't make important parameters directly sensitive to uncontrolled parameters of your components. And since the stability of the entire system depends on the position of this zero, the worst thing to do is to make the zero dependent on something like an ESR, which is a poorly controlled parameter and is parasitic anyway. Because small or even large changes of the ESR make correspondingly large changes in the stability margin, so that's violating the second answer to that question: how much margin do you need? It's directly sensitive to an uncontrolled second order parameter. So that's a horror story, because it's a combination of all of the worst things that you can do. And it's especially ironic, isn't it, because the second vendor was giving them a better capacitor. So, again, this is a reminder of how important it is to do these little pieces of design-oriented analysis, so you can keep control of these second-order effects and be sure that your margins and your tolerances are okay.